Hello, and welcome back to my next of a series of videos for Calculus BC at San Ynez High School. This is section 9.1 Power Series. I'd like to thank Greg Kelly at Hanford High School for, I'm not even sure, Hanford, Texas, I believe, for making his PowerPoint presentations available. I'll have a link on my webpage to his original presentation so that you can print that out if you prefer. So let's go ahead and get started. We'll start with a square that's 1 unit by 1 unit. If we take half of that square, then we have 1/2, plus half of what's left over is 1/4. Half of, again, what's left over is 1/8, plus 1/16, plus 1/32, plus 1/64, etc. We can keep dividing it up. And you can see from the graphic that eventually, for all practical purposes, we'll have included every bit of area, and therefore this series would converge to be 1 unit. So this is an example of an infinite series because it keeps going, yet it converges. It approaches a limiting value. Many series do not converge, like the harmonic series, 1/1 plus 1/2 plus 1/3 plus 1/4, etc., does not converge. It actually just approaches infinity. In an infinite series, we can have an infinite series that's a sub 1 plus a sub 2 plus a sub 3. Well, each of those are the terms of the series. And it can be written in sigma notation as the sum from 1 to infinity of a sub k. A sub n is the nth term. In the partial sums, that's adding up like the first term or the first two terms, etc. So s sub 1 is a sub 1. Partial sum s sub 2 is a sub 1 plus a sub 2, etc. S sub n would be the nth partial sum, the sum of the first n terms, could be denoted as k equals 1 to n of a sub k. And this is called the nth partial sum. If s sub n has a limit as n approaches infinity, then the series converges. Otherwise, it diverges. Let's take a look at a geometric series. In a geometric series, each term is found by multiplying the preceding term by the same number r, which is the common ratio. So we can write it as a plus a times r plus a times r squared plus ar cubed plus etc. And notice one thing interesting to note here. As you're doing this notation, make sure that you do plus dot 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 plus. It's actually something that apparently they're picky on grading. So you want to make sure you pay attention to that. You wouldn't want to lose a point on the AP exam for not doing that. This can be written as the infinite sum from 1 to infinity of a times r to the n minus 1. And note again, since you're starting with a times r to the 0, but you're starting off with n equals 1, that's to the n minus 1 power. Be careful to pay attention to that. So the partial sum of the first n terms of a geometric series can be written as s sub n is equal to a plus ar squared plus dot 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 plus ar to the n minus 3, n minus 2, n minus 1, etc. So remember, a times r to the n minus 1 is the last term. If you want to find the formula for a partial sum of a geometric series, this is something I added to Greg Kelly's PowerPoint presentation. So take a look at this. We can write the partial sum just like we did before. And then let's multiply both sides of that equation by r. So we'll get r times s sub n equals a to the r plus ar squared, so on. And notice what we have left over here. Pointing to this, we have an a left. We have an a here that doesn't match these, and we have an ar to the n that doesn't match any up there. But if we go ahead and subtract the bottom line from the top line, you'll see we get s sub n minus r times s sub n. So that's subtracting the left-hand side is equal to, again, the only terms that don't match up are the first term from the top one and the last term from the bottom one. So then we can solve by factoring out s sub n. We can get s sub n times r 1 minus r equals a times 1 plus r to the n, factoring out the a on the other side. Then divide both sides by 1 minus r, and we get a formula for the partial sum of a geometric series. All right. right, so that's important. You should make sure you memorize that. All right, let's go on to the next piece. The sum of an infinite series. So if we take that series and we go out to an infinite number of terms, so remember this is our partial sum that we just found the formula for. If we take the limit of that as n approaches infinity, well, it will converge if and only if r is less than 1. Actually, the absolute value of r is less than 1. And so if we assume that the absolute value of r is less than 1, then this would converge to a over 1 minus r. Again, if you think about it, this r to the n, if r is something less than 1, like in between 0 and 1, if you keep multiplying by itself over and over again, it gets smaller and smaller and smaller. So that's why that piece is approaching 0. Okay, and so the interval convergence, by the way, is for r between -1 and 1. So for a geometric sum series to converge, the ratio has to be between, the common ratio has to be between -1 and +1. Okay, let's do an example. Let's find the sum of the infinite geometric series 3 over 10 plus 3 over 100 plus 3 over 1,000 plus 3 over 10,000, etc., going on forever. Okay, so one way to look at this is we convert them all to decimals. You can see that we have this nice little pattern. It's 0.3 plus 0.03 plus 0.003, etc. And that would add up to 0.333 repeating, which of course is 1/3. Another way we could do it is look at our formula we just got, a over 1 minus r. And in this case, the common ratio is 1/10, and the first term is 3/10. So 3/10 over 1 minus 1/10, again, a over 1 minus r, is equal to 3/10 over 9/10, which simplifies to 3/9, which is also 1/3. So you see we got the same answer, adjusting it 2 different ways. All right. Next, let's do another example. We're finding the sum of the geometric series. Here, 1 minus 1/2 plus 1/4 minus 1/8. You can see that the common ratio is -1/2. So if we do a over 1 minus r, we would get 1 over 1 minus -1/2, which then ends up being 1 over 1 plus 1/2, which is 1 over 3/2, which is 2/3. So this series converges to 2/3. Last example for this video. Let's find the sum of this geometric series, where we're doing 1 plus x squared plus x cubed, so on. So you can see that we're just multiplying each one by x. This is the really common power series of each time we're just multiplying by x. Okay, so as long as the absolute value of x is less than 1, and our common ratio is x, then 1 plus x squared plus x cubed would converge to, using a over 1 minus r, 1 over 1 minus x. Okay, and the more terms we use, the better approximation we would get for this convergence. So this is a really important series. It's one of them we need to memorize. But it's really easy to memorize because you can always go back to a over 1 minus r to redevelop it. All right, I'm going to stop here, and I'll have another video to continue this lecture. Thanks so much for listening, and I hope these are helpful for you.